Imagine draining the oceans, every last drop, only to find a planet you've never seen before. A world stitched together by a 40,000-mile mountain range bigger than anything on land. Volcanoes rise in the dark like half-finished islands. Chimneys boil mineral-rich water into entire ecosystems that glow with life no sunlight has ever touched. Earthquakes crack the seafloor like tectonic arguments. Trenches swallow old crust whole. And through it all, underwater mountains quietly boss ocean currents, reshape the chemistry of the seas, and guide life in ways we're only beginning to understand. This is the hidden architecture of our world. The deep-sea spine that builds, breaks, and rebuilds the planet beneath our feet. And today, we're diving into it. If you thought the surface of Earth was impressive, wait until you see what it's been hiding. Imagine floating on the calm surface of the ocean, that massive blue blanket stretching in every direction like the planet's largest and most underrated comforter. Nothing seems hurried down there. The waves roll, the sun glints, and everything quietly pretends that this is all there is. But the ocean, as it turns out, is a world-class magician. It performs the greatest disappearing act on Earth every single day by hiding the biggest mountain range our planet has ever grown. And it hides it so well that if you could drain the oceans, you would suddenly be standing in front of a jagged, twisting, 40,000-mile-long chain of mountains that makes the Himalayas look like they're still in training. This is the part where the ocean would probably shrug and say, "Oh, you noticed?" Most people imagine the deep sea as a wide, flat, monotonous plain, like a parking lot someone forgot to put asphalt on. Instead, it's a landscape of peaks, valleys, cliffs, ridges, fissures, and geological oddities that seem like someone let the planet doodle freely for a few billion years. And right in the middle of all that doodling is the mid-ocean ridge, the planet's grand unbroken mountain system that stretches across the globe like Earth accidentally left a zipper running down the middle. If the continents are the suit, this is the seam holding everything together. The wild part is that we didn't even know it existed until frighteningly recently. In cosmic terms, we learned about it 5 minutes ago. Even in human terms, we found it long after we figured out electricity, wrote symphonies, and invented the sandwich. The ocean kept this ridge a secret. Not because it's shy, but because it knows we humans have a habit of poking things until they break. But before we wander too far into the ridge itself, let's hover in that moment of revelation. The instant humanity realized the ocean floor wasn't just a soggy version of Kansas. Picture the early days of deep ocean exploration, long before we had fancy sonar mapping, remotely operated vehicles, or satellites that can detect tiny shifts in the water's surface. Back then, if you wanted to know what the bottom looked like, you lowered a weighted rope and hoped it didn't snag on some creature with enough teeth to resent your intrusion. But whether by weighted ropes, war-era sonar, or the curiosity of scientists unwilling to accept boredom, we eventually stumbled upon something vast, something continuous, something downright monumental lurking beneath the waves. And that is where our story begins. Not with the mountains themselves, but with the astonishment that they were there at all. Because the truth is, the ocean doesn't present itself as a place with mountain ranges. It presents itself as a place where fish do things, waves crash, and people lose expensive sunglasses. Yet beneath all that daily ocean business is an entire chain of mountains, so long it could wrap around the planet more than once. It arcs from the Arctic Ocean down through the Atlantic, snakes around the tip of Africa, cuts across the Indian Ocean, skirts Australia, and keeps winding through the Pacific, like Earth's personal attempt at drawing a continuous squiggly line. If this were a doodle competition, Earth would win. Standing at the edge of this invisible mountain range, well, not literally standing because we'd be under miles of crushing water. You might expect everything to look chaotic or violent. After all, this is where the crust of the Earth is actively being created, where molten rock rises, cools, and becomes brand new seafloor. But strangely, the surface above remains serene. You could be sipping lemonade on a calm afternoon, while the planet is essentially forging new land beneath your feet, as if it were casually baking fresh crust, like it had a geological bakery hidden under the waves. The ocean is very good at keeping a straight face while doing something dramatic. And that contrast between the quiet surface and the wild hidden world below is what pulls us into this journey. It's like living above a gigantic secret city and never realizing it because the entrance is locked behind 3 miles of water and a strict no-tourists policy. But once you learn it's there, you cannot unsee the possibility of peaks rising in the darkness, valleys plunging deeper than the Grand Canyon, and volcanic activity painting the ocean floor with new shapes every day. Suddenly, the ocean stops being just water and becomes a whole new continent we forgot to map. So let this be the beginning of our descent, the moment we lean over the proverbial rail and squint into the unknown. The mountains below are real. They are massive. They are alive in a geological sense, heaving and shifting and growing at speeds so slow they make glaciers look impatient. And though they are hidden, they are not silent. They shape currents, birth ecosystems, and sculpt the underwater world in ways we're only beginning to understand. As we move from one chapter to the next, we're going to travel along this submerged spine of the Earth, not as divers or submariners, but as curious wanderers drifting through the planet's most secretive masterpiece. And if the ocean insists on being shy about it, then too bad. We're pulling back the curtain anyway. Long before we sent satellites into orbit or robotic submarines to poke around the deep, humanity tried to understand the ocean floor with the scientific equivalent of closing one eye and squinting really hard. Picture a crew of sailors tossing a weighted rope over the side of a ship, watching it sink and declaring, with absolute confidence, "Yup, definitely wet down there." That was early oceanography, a bold blend of courage, curiosity, and what can only be described as extremely optimistic guesswork. If the ocean floor were a mystery novel, the first people trying to read it were missing half the pages and the bookmark. But even with primitive tools, strange clues began to surface, clues that suggested something enormous hid beneath those rolling waves. In the 18th and 19th centuries, the ocean held its secrets with the smugness of a cat guarding a locked room. Ships crossed the Atlantic and Pacific endlessly, yet no one suspected that an entire mountain chain lurked beneath the keels of wooden vessels. Sailors, of course, were more concerned with storms, supplies, and not falling off the boat, so the seafloor wasn't exactly their top priority. Still, every now and then, when someone dropped a sounding line, basically a glorified rope with a chunk of metal at the end, it hit bottom sooner than expected. Other times, the rope dropped so far that the crew began to wonder whether the ocean might simply continue forever, straight into the underworld. Soundings were inconsistent, erratic, and occasionally alarming. But patterns slowly emerged, subtle as whispers. The first real hint that something unusual stretched across the Atlantic came from attempts to lay the first transatlantic telegraph cable. Engineers, who thought the ocean floor was nice and flat and cooperative, discovered instead that it was moody, uneven, and about as predictable as a sleep-deprived professor. As they dragged their equipment across the seabed, the cable snagged, dipped, then unexpectedly climbed. It behaved as though it were being hauled across hills and valleys, hills that shouldn't have existed, valleys no one had seen, and slopes that suggested the ocean had been hiding an elaborate terrain map all along. One of the pioneers who helped piece together these first clues was Matthew Fontaine Maury, a naval officer who had a talent for noticing things most people ignored. Maury never saw the ocean floor with his own eyes, but he collected ship logs that mentioned unusually shallow or deep measurements. He treated the ocean like a puzzle, and the sounding ropes like scattered hints. Using them, he proposed that there might be something significant beneath the surface, some ridge-like rise that stretched across the Atlantic. It was a bold claim at the time, considering he was trying to describe an underwater mountain while armed with little more than frayed ropes and sailors' scribbled notes. But bold claims are often where science begins. Through the late 19th century, technology improved at the pace of a sleepy tortoise. But even the smallest advancements helped. A device known as the sounding machine arrived, a metal tube lowered by a single wire instead of a rope. For the first time, scientists could get somewhat accurate depth measurements without the rope drifting sideways, getting tangled, or being chewed on by a curious fish. Yes, that happened multiple times. The ocean does not respect scientific equipment. Still, the real turning point didn't arrive until the early 20th century with the invention of echo sounding. Suddenly, instead of dropping something down and waiting like a fisherman with questionable patience, scientists could send sound pulses into the deep and listen for the returning echo. It was revolutionary. The ocean floor finally spoke back, even if its voice was a metallic ping that sounded like someone tapping a saucepan underwater. These echoes revealed more than mere depth. They outlined slopes, plateaus, and irregularities. When scientists stitched these soundings together, they saw something astonishing. A long, elevated ridge running through the Atlantic like a hidden backbone. But before we leap ahead to the later precision of mapping, it's worth lingering in this marvelous era of discovery when scientists were essentially reverse engineering the planet with limited tools and abundant imagination. Many researchers published early maps that looked less like accurate charts and more like enthusiastic doodles. Some ridges were placed in the wrong spots. Some depths were wildly incorrect. At one point, a supposed mountain turned out to be nothing more than a misreading caused by a malfunctioning cable winch. But science is forgiving. Mistakes are just stepping stones wearing funny hats. The beauty of this early period is that no one truly knew what they were about to uncover. They sensed irregularities, suspected the presence of major structures, but couldn't yet see the grand scale. It was like hearing distant thunder without knowing it belonged to a storm spanning the entire sky. Every new measurement chipped away at the mystery, revealing hints of something continuous and vast. Some scientists theorized that these underwater rises might be part of a global system. Others believed they were isolated features. No one realized yet how astonishingly interconnected they were. As the 20th century progressed and measurements grew more precise, an idea began to form. Tentative at first, then bold, then impossible to ignore. These strange rises didn't merely dot the ocean floor. They stretched across thousands of miles. They connected from ocean to ocean. They might even wrap around the entire planet. Something colossal and hidden was drawing a line through the deep, and humanity had only just noticed, because finally, our tools were good enough to tell the ocean, politely, that secrecy time was over. What makes this chapter of history so compelling is that it captures that moment of dawning awareness, the realization that the seafloor wasn't passive or flat or featureless. It was dynamic, sculpted, folded, lifted, carved, and alive in a geological sense. It had been hiding mountains the entire time, and humanity had been sailing over them for centuries, blissfully unaware that the ocean was sitting on a secret so big it required an entire global expedition just to whisper its first hints. And with those early whispers, our journey truly began. If you could peel back the ocean like the world's heaviest blanket, the first thing that would leap into view, other than the shocking amount of empty darkness, is a ridge. Not a small one, not a polite one, but a colossal, sweeping, continuous mountain chain that stretches across the entire planet. It slithers through the oceans the way a spine runs down a back, except in this case, the spine is 40,000 miles long, and the back is the Earth itself. This is the mid-ocean ridge, the world's most committed overachiever, quietly looping from ocean to ocean like it has somewhere very important to be. If Earth ever went to a chiropractor, this ridge is exactly what the doctor would look at and say, "Wow, when was the last time you stretched?" The ridge begins, depending on how you define begin, near the Arctic, curling its way through the Atlantic before branching into the Indian Ocean, then bending into the Pacific, like it's signing a dramatic geological autograph. What makes it breathtaking isn't just its size, but its constancy. Land mountain ranges are impressive, sure, but they're scattered. They rise, fall, break off into smaller groups, or fade into plateaus. The mid-ocean ridge? It refuses to be anything but continuous. It's the one mountain range on Earth that seems determined to win every endurance contest ever invented. And unlike land-based mountains that scrape against winds and weather, the ridge exists in total darkness, beneath crushing pressure and freezing temperatures. Yet even under these extreme conditions, it thrives. Not in a biological sense, that comes later in other regions, but in a geological one. This is a place where the crust is young, energetic, and constantly reshaping itself. If land continents are old libraries filled with ancient stories, the ridge is a printing press churning out brand new pages. Every bit of the ridge is in motion, stretching, widening, or shifting as molten rock rises from below and creates fresh seafloor. It is, quite literally, the world's longest construction project. Geologists sometimes describe the ridge as a boundary where tectonic plates move apart, but that description undersells the drama. Think of the mid-ocean ridge as the seam where the Earth gently, persistently unzips itself, making room for new material. It is a place where the planet expresses its inner molten personality. Magma wells upward, cools into rock, and is shoved aside by more magma moving in behind it. A cycle so steady and reliable it's almost emotional. If mountains could read self-help books, this ridge would have highlighted every section about growth and renewal. The shape of the ridge is anything but uniform. In some places, it rises as towering, rugged mountains that would rival any terrestrial range if they weren't buried under miles of water. In other areas, the ridge broadens into wide, gentle swells that seem less like mountains and more like the ocean floor, casually puffing its chest. Sometimes it breaks into segments divided by fractures, making it look like an ancient backbone held together with nature's version of improvised repairs. If you ever wanted proof that the Earth has been tectonically active for billions of years, the ridge is that proof, etched across the seafloor like the planet's signature. Perhaps the most captivating part of the ridge is its sheer consistency. It doesn't hesitate, doesn't skip sections, doesn't suddenly vanish. It just keeps going, and going, and going. Even where the ridge dips deeper or grows shallower, its presence remains unmistakable. It almost feels intentional, as if the planet wanted to draw one continuous line across its oceans and refused to lift the pencil. When scientists first mapped it in detail, there was a collective pause, an astonished moment in which geographers realized they were seeing the world stitched together in a way no one had ever imagined. Oddly enough, this enormous feature doesn't always present itself as sharp or jagged. At times, its peaks are surprisingly rounded, a result of constant volcanic creation smoothing things out. Other times, the ridge splits open into dramatic rift valleys, long, deep troughs where the crust is being pulled apart. These valleys can stretch for hundreds of miles, bordered by cliffs so steep that if they existed on land, tourists would flock to take selfies in front of them. Down in the deep, however, the only witnesses are drifting particles, the occasional exploratory robot, and whatever resilient creatures happen to wander nearby. What makes the ridge even more spectacular is that it is not simply a geological monument frozen in time. It is alive with motion. The plates on either side move apart at varying speeds, pulling the ridge with them like an ever-widening scar. While human lifetimes are too short to notice this expansion directly, the evidence accumulates in the rocks themselves. Young crust forms at the ridge, ages as it moves outward, and eventually drifts into older, cooler territories. It's a slow dance, so slow that if you tried to watch it in real time, you'd fall asleep 3 times before anything measurable happened. But that slowness doesn't lessen the magnitude of the process. In a way, the ridge offers a humbling reminder of just how dynamic our planet really is. We think of continents as stable, mountains as immovable, and oceans as vast but unchanging. Yet beneath the surface lies this monumental system, working tirelessly. The mid-ocean ridge is the heartbeat of the planet's crust, pulsing with energy that shapes the seafloor, influences ocean chemistry, and quietly orchestrates the layout of the oceans themselves. By the time modern mapping revealed its full reach, scientists realized that we had been floating above one of the greatest natural structures in the universe, completely unaware. It is Earth's secret architectural masterpiece, hidden not because it's modest, but because 3 miles of seawater make for an excellent disguise. And so the ridge continues beneath us, stretching, growing, shifting, like the world's most persistent reminder that our planet is far from still. To understand seafloor spreading, you have to picture the planet doing something that sounds impossibly dramatic, but plays out so slowly it makes continental drift look impatient. Deep beneath the ocean, at the mid-ocean ridge, Earth is constantly manufacturing new crust. Not metaphorically, literally. Magma rises from the mantle, cools the moment it hits the frigid seawater, and becomes solid rock. Then more magma rises and shoves that rock aside to make room for the next batch. It's a non-stop process, like the planet is running a cosmic bakery that churns out fresh crust 24 hours a day with absolutely no interest in stopping for holidays. If Earth wore an apron, this would be the place to find flour all over it. But the magic starts far below, long before the magma reaches the ridge. Deep in the mantle, heat from radioactive decay and leftover energy from Earth's formation keeps rock warm enough to behave like a very thick, extremely grumpy pudding. This mantle material moves in slow, rolling convection currents, upward in some places, downward in others. Where heat rises, the pressure decreases just enough for some of that rock to partially melt. This melt gathers into pockets, and those pockets do what all buoyant things do. They start climbing. Not quickly, of course. Magma travels upward at a pace that would make a snail impatient, but travel it does. When that magma reaches the base of the crust beneath the mid-ocean ridge, it begins to exploit weaknesses, cracks, channels, and tiny paths carved by geological stress. As plates pull apart at the ridge, those cracks widen, giving magma a direct invitation to rise toward the surface. The process isn't explosive like a volcano on land. It's more like the quiet, steady refill of a fountain. Think of the magma chamber as a patient chef, lifting each ladleful of future rock into position. The moment magma touches seawater, the temperature difference is so extreme, it's like dropping molten iron into ice water. The magma chills, crystallizes, and hardens into basalt almost instantly. New crust is born in the blink of an eye, though the crust doesn't stay right at the ridge. As even more magma rises behind it, the newly formed rock gets nudged sideways, inch by inch, year by year. Over millions of years, that inching becomes hundreds of miles. What begins as glowing orange liquid ends up as dark, dense seafloor, stretching all the way to the edges of the ocean basin. The spreading itself is shockingly organized, almost rhythmic. On either side of the ridge, magnetic minerals in the cooling basalt lock in the direction of Earth's magnetic field at the moment they solidify. Because Earth's magnetic field has flipped back and forth many times throughout history, these minerals create alternating stripes, like zebra patterns, on the seafloor. These stripes extend for thousands of miles, matching perfectly on both sides of the ridge, as if the Earth thoughtfully provided barcodes to help scientists check its work. No one asked for geological patterns this tidy, but the planet delivered anyway. As the crust moves outward, it ages. Young crust near the ridge is warm, buoyant, and elevated, but the farther it drifts, the more it cools. Cooling makes it contract and sink, giving older crust the slightly droopy posture of something that has accepted its responsibilities. This subtle sinking shapes the entire layout of the ocean floor, forming wide basins bordered by rising edges. If you could watch the seafloor age in time-lapse, it would look like someone ironing a sheet that slowly gets heavier at the edges. The creation of new crust also plays a quiet role in controlling the chemistry of seawater. As hot magma cools into solid basalt, it reacts with surrounding water, trapping some elements while releasing others. Minerals move in and out of the crust like customers in a busy marketplace. Over time, this subtly influences the composition of the oceans, a constant negotiation between rock and water that has been going on for hundreds of millions of years. It is not dramatic, and yet it is vital. The seafloor is always in quiet conversation with the sea above it. One of the most remarkable aspects of seafloor spreading is its consistency. Despite variations in spreading speed, some ridges widen at a few centimeters per year, others at a handful more. The process itself is astonishingly reliable. There is always magma rising. There is always crust forming. There is always motion. Even when the ridge looks calm and unchanging, the work continues in the dark, uninterrupted by storms, seasons, or the whims of surface life. You could hover above it for a lifetime and never see a flare or explosion, yet beneath that calm lies one of the most powerful engines shaping the Earth. What makes the process even more beautiful is that it connects every ocean on Earth into one continuous system. Though each segment of the ridge has its own personality, different heights, shapes, and spreading speeds, they all participate in this grand, global choreography. New crust forms at the ridge, slides outward, cools, and eventually returns to the mantle elsewhere in the world. It's part of a larger cycle that recycles the planet's surface, maintains ocean basins, and keeps continents moving like extremely stubborn puzzle pieces. And through it all, the ridge keeps baking crust with the steady confidence of a seasoned chef. No rush, no panic, no drama, just a quiet, relentless process that has shaped the face of the Earth in ways we're still learning to fully appreciate. Seafloor spreading is the pulse of the deep, the conveyor belt of our planet's geology and the reason the oceans look the way they do. It may happen at a pace too slow to feel, but its impact is written across the entire world. The first time scientists stumbled upon hydrothermal vents, they were expecting a chilly, barren landscape, an underwater desert, where the only excitement would be the occasional confused fish. Instead, they found something so dramatic, it felt as if the ocean had been hiding a secret furnace at the bottom of the world. Along the cracks of the mid-ocean ridge, water superheats, minerals erupt upward in dark plumes, and bizarre chimneys grow from the sea floor like metallic skyscrapers, built by a very enthusiastic blacksmith. If the deep sea had a kitchen, these vents would be the kettles that never stop boiling, hissing, or generally behaving like appliances with anger management issues. To appreciate these hydrothermal vents, you have to imagine the journey of water that slips into the seafloor. Picture cold seawater sinking through fractures and porous rock, drifting downward like a lost tourist who took one wrong turn and refused to ask for directions. As it descends, the water encounters rock heated by underlying magma. Temperatures climb rapidly, so rapidly that the water would scream if it had vocal cords. But because the enormous pressure prevents it from boiling, the water simply heats past the normal boiling point while staying liquid. It becomes something new. A superheated fluid packed with dissolved minerals, metals, gases, and enough stored energy to make any kettle on land feel inadequate. Eventually this water, now far too hot and heavy to stay put, begins its return trip upward. It rises through vents, cracks, and channels carved by the ceaseless shifting of the ridge. When it finally blasts back into the open ocean, it meets cold seawater again, and the sudden temperature drop triggers an instant chemical reaction. Minerals dissolved in the superheated water precipitate, forming clouds of dark particles. These particles puff upward like underwater smoke. Except there's no combustion here, just chemistry, throwing a surprise party. The result is the iconic black smoker, a chimney spewing mineral-rich plumes that look like a deep-sea volcano vaping dramatically in the darkness. These chimneys grow quickly, stacking mineral deposits layer by layer. Some rise dozens of meters tall, sculpted from iron sulfides and other compounds that crystallize the moment they hit cold ocean water. They look like Gothic towers from a sunken fantasy city, each one intricately shaped by the constant flow of superheated water. Nearby, where the chemistry differs, white smokers appear, emitting lighter-colored plumes made of barium, calcium, and silicon. These have a slightly gentler aesthetic, still boiling, still dramatic, but more like underwater teapots that prefer chamomile over espresso. Despite their volcanic personality, hydrothermal vents are astonishingly fragile. A shift in temperature, a change in the flow of water, or a slight variation in chemistry can cause a chimney to collapse. When one falls, another soon grows in its place, as if the vents are determined to rebuild their architectural masterpieces, no matter how many times nature knocks them down. They are among the few geological features on Earth that grow visibly within human lifetimes. Watch long enough, and you'd see vents sculpt themselves like time-lapse pottery. What makes these vents so extraordinary isn't just their heat or their mineral output. It's that they rewrite the rules of what life needs to survive. The deep ocean is a world without sunlight, and hydrothermal vents provide the energy that light would normally deliver. Though we'll explore these ecosystems more deeply in other chapters, it's worth noting here how the vents themselves create the stage on which that life appears. They release hydrogen, methane, and other compounds that microorganisms can use as fuel. In this pitch-black realm, chemistry replaces photosynthesis. Instead of sunlight driving life, it's the vent fluids themselves, a complete role reversal that would make any biologist do a double take. Standing near a hydrothermal vent, well, metaphorically, unless you enjoy instant vaporization, you'd witness an environment of extremes. Water temperatures can shift from near frozen to over 400 degrees Celsius within a few feet. Pressures are so high they would crush submarines not built for the challenge. Minerals crystallize in real time. Metal-rich plumes drift upward like underwater storm clouds. The landscape is both serene and chaotic, like a natural forge that forgot it wasn't supposed to be beautiful. These vents also act as windows into Earth's interior. By studying them, scientists learn about the composition of the mantle, the chemistry of ancient oceans, and the conditions that may have sparked early life. Some theories propose that life on Earth began in environments much like these, places where minerals and heat danced together in ways that encouraged complex chemistry. If that's true, then hydrothermal vents aren't just chimneys. They're possibly the original laboratories of existence, where nature had both the heat and the ingredients to run its first experiments. Despite how dramatic they are, vents are scattered, forming along ridge segments where the crust is most fractured. They appear, disappear, migrate, and rebuild as the geology shifts. Every vent field is temporary in the grand scheme of things, though temporary down here still means thousands of years. They live long enough to shape ecosystems, craft minerals, and release chemicals that spread through the deep, but not long enough to be considered permanent monuments. They are dynamic, evolving, and wonderfully unpredictable. You could almost imagine the vents whispering to the ridge, "We'll take your heat and do something interesting with it." And the ridge, busy with spreading the seafloor, would respond with a weary sigh. "Fine, just don't melt anything important." Hydrothermal vents are the ocean at its most theatrical. A reminder that even in the darkest, coldest corners of the world, Earth still finds a way to create heat, structure, and a bit of geological flair. They are chimneys of the deep, kettles always on the verge of boiling over, and one of the greatest spectacles hidden beneath the waves. If hydrothermal vents are the ocean's hidden furnaces, then the ecosystems that surround them are the deep sea's most astonishing plot twist. Down in a world where sunlight never arrives, where the darkness is so complete it feels like the universe forgot to install a switch, life should be scarce. It should be minimal, quiet, maybe a few microbes politely going about their business. Instead, these vents host bustling, vibrant communities so strange that when scientists first saw them, they reacted with the same energy you might have upon discovering a carnival in your basement. Not only were these ecosystems thriving, they were thriving in a way no one expected, fueled not by sunlight, but by chemistry, heat, and the astonishing adaptability of life. At the center of these communities are the microbes, tiny masterminds that do what plants do on land, but with an entirely different toolkit. Without sunlight, photosynthesis is impossible. So the microbes turn to something else: chemosynthesis. They take chemicals spewing from the vents, things like hydrogen sulfide and methane, and convert them into energy. Imagine running a city not on solar power, but on the fumes from a volcanic smokestack. These microbes do it effortlessly, and in doing so, they create the foundation for every other creature gathered around the vents. Among the most iconic residents of this world are the giant tube worms, creatures so peculiar they look like evolution tried something entirely experimental and forgot to add final touches. They tower in clusters, white chitinous tubes rising several meters high, with bright red plumes sticking out of the top like they're all attending the same extravagant gala in strange formal attire. Tube worms are the organisms that give the whole scene a surreal, almost dreamlike quality. They look like decorations at a deep-sea award show, and if there's one creature that seems to have skipped evolution's dress code, it's these towering, noodle-like beings. Tube worms survive through a remarkable partnership. They have no mouth, no stomach, and no conventional way to digest anything. Instead, inside their bodies, they house special bacteria that perform chemosynthesis for them. The worms simply absorb chemicals from the vent water, supply them to their internal bacterial tenants, and receive nutrients in return. It's a symbiotic arrangement, so efficient, it could make any landlord jealous. The worms provide real estate, and the bacteria provide food. It's life built on teamwork, trust, and a lot of sulfur. But tube worms are far from the only residents of these alien neighborhoods. Surrounding them are creatures so varied and unusual that calling them bizarre feels like an understatement. There are vent crabs, small, pale, sometimes nearly transparent, scuttling along the mineral chimneys like the world's most determined maintenance crew. They feed on whatever they can find. Dead worms, microbial mats, bits of organic drift. Their lives are spent in darkness, their world illuminated only by the shimmering waves of superheated water escaping from the vents. Then there are the vent shrimp, creatures that seem custom-built for survival in such an extreme environment. Some species have specialized sensors on their backs that detect faint heat signatures, an adaptation that helps them avoid straying into water hot enough to cook dinner instantly. Others host chemosynthetic bacteria directly on their bodies, farming them like tiny living gardens. These shrimp crowd around vents in enormous swarms, shifting and pulsing like clouds of living metal. Vent mussels and clams also stake out their territory, clustered in groups atop rocky outcrops, relying on their own symbiotic bacteria. Unlike their shallow water relatives, these deep-sea versions look tougher, as if they've been carved from stone rather than shell. They draw in chemical-rich water through their tissues, letting their microbial partners extract nutrients. It's a lifestyle that requires remarkable resilience, especially in an environment where temperatures can swing wildly over just a few inches. One of the strangest animals found near vents is a species of snail that seems to have taken the phrase "armor up" to heart. Called the scaly-foot snail, it builds its shell and scales out of iron sulfides. That's right, metal. This snail literally incorporates minerals from vent water into its body, creating a suit of armor that would make medieval blacksmiths weep with envy. It clings to rocks near the vents, its metallic plates glinting faintly in the faint chemical shimmer. If superheroes existed in the deep sea, this snail would absolutely demand a cape. The most mind-bending part of all these creatures isn't just their strange appearances, but the simple fact that they survive in conditions that defy nearly every rule. Life seems to follow elsewhere. Temperatures swing dramatically. Pressures soar to levels that would crush submarines. Toxic chemicals drift constantly through the water. And yet the ecosystem flourishes. It grows. It evolves. It builds towers of biomass in the dark, all without ever using sunlight. That alone overturns centuries of assumptions about what life requires. Watching this community is like observing a secret festival in a place we once believed was empty. Every creature has found a role. Every microbe contributes to the food web. Every vent structure offers new space for life to establish itself. It's a system driven entirely by chemistry, proof that life doesn't need many of the things we once thought were absolutely essential. It just needs opportunity, innovation, and a willingness to improvise. And perhaps that is the magic of hydrothermal vent ecosystems. They show us that life is far more adaptable, far more imaginative than we ever expected. In a world without sunlight, life learned to glow through chemistry. In a vacuum of impossible conditions, life invented new strategies. And where we once saw only cold darkness, there is now a thriving metropolis of creatures. From tube worms in flamboyant outfits to iron-plated snails and heat-sensing shrimp, all proving that evolution is not only creative, it has a delightful sense of humour. If hydrothermal vents are the chimneys of the deep sea, then black smokers and white smokers are the two rival restaurants competing for customers in a neighbourhood where no one can see, smell, or hear anything. They stand only a few meters apart, puffing out their mineral-rich plumes like competing chefs, showing off their signature dishes. The deep sea, apparently, was not content with just one type of boiling geological fountain. It needed variety, contrast, and a full menu, even if the only patrons are bacteria and the occasional confused shrimp. These vents may not serve food in the traditional sense, but they certainly serve chemistry with flair. Black smokers are the most dramatic of the two. Their jets of superheated water look like columns of soot rising from underwater chimneys, which is how they earned their name. But the smoke isn't smoke at all. It's an eruption of tiny mineral particles, mostly sulfides, that precipitate as soon as the 400-degree fluid meets near freezing seawater. Picture a boiling cauldron in a haunted house, except the cauldron is a chimney made of minerals, and the ghosts are actually tiny bits of iron and magnesium. These vents release so many particles that the water turns as dark as ink, deep, swirling clouds drifting upward in twisting spirals. The chemistry inside black smokers is fierce. The water rushing out is practically a chemical soup, loaded with iron, copper, zinc, and other metals dissolved into the hot fluid. Hydrogen sulfide, a gas that smells like rotten eggs on land but goes mercifully unnoticed in the deep sea, dominates the mix. When this fluid meets cold seawater, the minerals resolidify. Iron sulfide, for instance, forms the bulk of the dark plumes. Over time, these particles pile up, creating towering chimneys that grow like mineral stalagmites, except upside down and much faster. These chimneys can become enormous. Some rise as tall as buildings, shaped by constant layers of metal-rich deposits. As the chimney's walls grow thicker, they channel the hydrothermal flow upward, reinforcing the structure while also forcing the vent to adapt. The result is an ever-changing skyscraper of mineral formation, always growing, always eroding, always rebuilding itself. If cities were built this quickly, real estate agents would cry tears of joy. White smokers, on the other hand, are the gentler cousins in this chemical family. Instead of blasting out dark clouds, they release pale, milky plumes, rich in lighter minerals. Their waters contain compounds like barium, silicon, and calcium, substances that produce the white, cloudy appearance when they solidify. These vents tend to be cooler than black smokers, although cooler is relative. They're still hot enough to ruin any submarine unprepared for their temperatures. If black smokers are the fiery grill masters of the vent world, white smokers are the delicate pastry chefs, whipping up lighter, creamier mineral soufflés. Unlike the towering black smoker chimneys, white smoker structures often form more intricate, branching shapes. Their mineral deposits create delicate spires, porous walls, and labyrinthine channels. The formations sometimes resemble coral reefs, sculpted out of ghostly stone. They are paler, more brittle, and more fragile than the bold black structures nearby. And yet, they too create pockets of life. Microbes cluster around them, using the chemicals in the plumes to fuel their existence. From a distance, the two types of smokers look like members of very different families, yet both are cut from the same geological cloth. The differences between black smokers and white smokers come down to chemistry and temperature. Black smokers reach higher temperatures, sometimes more than 400 degrees Celsius, because they tap directly into hotter pockets of water deep beneath the crust. These extreme conditions allow more metals to dissolve into the fluid. When the water meets the ocean, those metals drop out dramatically, forming the signature black clouds. White smokers, cooler by comparison, dissolve fewer metals but pick up more of the lighter minerals. Their emissions are rich in barium sulfate and silica, which create their pale colour. It's the geological equivalent of two kitchens working with completely different ingredient lists. If you were to imagine them as rival eateries, black smokers would be the heavy metal barbecue joint, while white smokers would be the artisanal cafe offering mineral lattes. Both types of vents depend on the same underlying process: seawater travelling down into the crust, heating up from contact with underlying magma, then surging back upward with a load of dissolved minerals. But subtle shifts in temperature, the surrounding rock composition, and the pathways the water takes produce enormous variations in the resulting structures. The deep sea, it seems, enjoys surprising even itself. Though they operate independently, black and white smokers often appear in the same general regions, clustered along zones where the crust is fractured enough to let seawater enter. These clusters form patchwork neighbourhoods, some vents, billowing dark plumes, others glowing faintly white. They can coexist peacefully, each maintaining its own chemical identity. But even within a single vent field, the balance can shift over time. A black smoker may evolve into a white smoker if its temperature changes or its chemistry alters. Vents are not static. They transform, rebuild, collapse, and change their mineral profiles, like performers switching roles mid-scene. The complexity of these structures provides countless microhabitats for deep-sea organisms. Crevices hold microbial mats. Shallow slopes shelter clusters of hardy animals. And the swirling plumes feed chemosynthetic bacteria drifting in the current. Each vent, regardless of type, becomes the center of its own small universe, an anchor point in the otherwise sparse deep-sea landscape. Black smokers and white smokers may look like competing attractions in a geological amusement park, but they are, in truth, complementary expressions of the same incredible process. Each one demonstrates how dynamic the ocean floor is, how heat and chemical reactions reshape the crust, and how life adapts to even the most extreme environments. And if you've ever wished for a restaurant run by minerals instead of chefs, just know the deep sea beat you to the idea millions of years ago. At first glance, the mid-ocean ridge looks like a single grand line running across the seafloor, a continuous thread stitching the oceans together. But get closer, much closer, and that clean line starts to break apart. The ridge doesn't stretch smoothly like a painter's confident brushstroke. Instead, it zigzags in abrupt, sideways offsets, as if Earth suddenly decided to experiment with avant-garde geometry halfway through assembling its underwater masterpiece. These jagged offsets are transform faults, and the long scars they leave behind are fracture zones, features that give the seafloor its fractured, restless character. If the ridge is Earth's spine, these faults are the crooked vertebrae, reminding us that the planet has never been particularly concerned with symmetry. To understand transform faults, Imagine two giant slabs of crust sliding past each other, like neighbours trying to squeeze down a narrow hallway without making eye contact. At the ridge itself, the crust is pulling apart, making room for new material. But because spreading doesn't happen uniformly everywhere along the ridge, some segments move slightly faster or slower, and that imbalance creates tension. Nature, being allergic to unresolved tension, cracks the crust in sideways breaks that offset one ridge segment from the next. These faults become the boundaries where the plates grind horizontally against one another. Slowly, relentlessly, with all the grace of two tectonic plates writing an awkward apology note through friction. The movement along a transformed fault is horizontal rather than vertical. Unlike a typical fault you might see on land, where rocks shift upward or downward, transformed faults involve sideways sliding. It's shearing, pure and simple, but don't let the simplicity fool you. The forces at play are immense. As the plates drag past each other, they generate stress that builds silently over decades or centuries before slipping suddenly. When they do, the energy release sends seismic waves racing through the water. Deep in the ocean, where light never reaches and where silence usually reigns supreme, these faults provide some of the loudest geological moments, like the earth clearing its throat a little too aggressively. Still, the most intriguing part of transformed faults is that they only actively slide along a short portion where the ridge segments offset. Beyond that sliding portion lie fracture zones, vast underwater scars stretching for hundreds or even thousands of miles across the seafloor. If transformed faults are the moments of motion, fracture zones are the lingering memories. Once the rocks move past the active faulting region and drift away from the ridge, they cool and lock into place, preserving the offset as a permanent line etched across the ocean floor. These lines can run astonishing distances, cutting through the crust like someone dragged a knife across a sheet of clay. From above, say, from a satellite altimetry map, the seafloor appears scratched with long parallel grooves. These grooves trace ancient fault lines, marking where plates once shifted and now drift quietly toward the edges of the ocean basin. Fracture zones don't move anymore, but they keep the geological handwriting of the mid-ocean ridge intact. They show where the crust formed at different times, where temperatures varied, and where the plates parted ways, not with a clean break, but with a series of staggered steps. What makes fracture zones especially fascinating is that they reveal the history of spreading in a way nothing else does. Each zone marks a boundary between crust of different ages and temperatures. On one side of the fracture zone, the crust might be younger, warmer, and slightly puffed upward. On the other side, older, cooler crust droops lower. The contrast is subtle but unmistakable, creating tiny variations in the seafloor's elevation. So tiny that only with precise measurements or deep-sea mapping can we fully appreciate them. Think of them as the stretch marks of plate tectonics, recording every shift and every tug the ocean floor has ever felt. Transformed faults also play an essential role in allowing the ridge to curve around the planet. Because Earth is round, the ridge can't simply run straight like a road across a flat map. It has to bend, twist, and adjust to the sphere it wraps around. Transformed faults enable that bending. They act as flexible joints connecting rigid ridge segments, letting the entire system fit neatly across Earth's surface without tearing unpredictably. Without these sideways offsets, the ridge would struggle to maintain its global continuity, and the ocean floor would look far messier. Impressive, perhaps, but geologically chaotic. While transform faults allow for sliding, the interior of fracture zones is cold, inactive, and quiet. But don't confuse quiet with unimportant. These zones affect ocean circulation by subtly altering the shape of the seafloor. Currents respond to even slight bumps and grooves, redirecting water flow along invisible paths carved into the crust. Over time, these redirected currents influence temperature distribution and nutrient movement, small tweaks that ripple outward into the broader ocean. From a geological standpoint, transform faults also introduce variety into the ridge environment. Some segments of the ridge are narrow and steep, others wider and more gentle. Much of this difference comes from how the faults offset the spreading centers. Some ridges are split frequently by large fault lines. Others stretch long distances before a single offset interrupts their continuity. Each setting produces its own landscape, a patchwork of slopes, valleys, cliffs, and steps that give the seafloor a rugged topography no human hand could replicate. Standing, metaphorically, at one of these faults is like standing at the seam between two moving continents, except everything is hidden beneath miles of water and total darkness. Here, the rock is cracked, bent, and twisted in ways that tell the story of immense forces at work. If you could run your hand along the rock face, you'd feel jagged lines where the crust scraped against itself. You might even feel the subtle difference between the two sides. One formed slightly earlier, one slightly later. There's a strange elegance in these faults. They aren't gentle features, nor are they the explosive vents or towering chimneys found elsewhere. Instead, they are the corrections, geology adjusting its math. While volcanic vents build, transform faults realign. While magma creates, faults accommodate. They are, in essence, the subtle engineers of the seafloor, allowing the ridge to express its full length without tearing itself apart. And in the grand gallery of the ocean floor, these zigzagging lines add character. They give the seafloor its flair, its asymmetry, its avant-garde geometry. Proof that even the deepest parts of the earth enjoy a little artistic expression. If the mid-ocean ridge were a treadmill, it would be the kind you step onto at the gym and instantly realize has a mischievous personality. One moment, it's cruising along at a gentle walking pace, and the next it's speeding up without warning, flinging your plans, and possibly you, into the nearest wall. This inconsistency is exactly what Earth does beneath the oceans. Some parts of the ridge spread apart quickly, creating new crust at an energetic sprint, while others plod along at the geological equivalent of an elderly stroll. The ridge system, in other words, can't agree on a single speed setting, and it has absolutely no intention of fixing its uneven pacing. Understanding why some ridges race and others dawdle requires zooming out to the engine behind all spreading mantle convection. Beneath the crust, the mantle moves in slow, looping currents driven by heat rising from the deep earth. Where these currents push strongly upward, more magma arrives at the ridge more quickly. More magma means more new crust, which means the plates get shoved apart faster. Fast-spreading ridges sit atop these vigorous mantle upwellings like surfers riding an especially eager wave. Meanwhile, ridges with weaker upwellings receive less magma, spread more sluggishly, and build their crust more reluctantly. Like a baker who keeps checking the oven door instead of letting the dough rise. But mantle flow isn't uniform across the planet. The speed and vigor of convection vary depending on temperature, composition, and the arrangement of plates overhead. Some parts of the mantle have hotter, more buoyant material rising from deeper layers. These produce ridges that spread at several inches per year, quick by geological standards. Other mantle regions are cooler or circulating differently, offering less molten material to the ridge. These give rise to slow-spreading segments that barely creep forward. The treadmill under the oceans, therefore, isn't malfunctioning. It just has parts that are powered by different-sized engines. The speed of spreading dramatically shapes the appearance of the ridge itself. Fast-spreading ridges tend to have smooth, wide profiles. Their magma supply is so steady and plentiful that the crust forms like soft, pliable dough, filling in gaps before rugged terrain can develop. The result is a broad, elevated dome rather than steep cliffs or deep valleys. If you could fly over one with perfect visibility, it would look surprisingly sleek, almost as though the seafloor had been polished by some meticulous underwater custodian. Slow-spreading ridges, on the other hand, are rugged, dramatic, and full of character. With less magma rising to fill the growing gap between plates, the crust has a harder time staying intact. It breaks, collapses, and fractures, producing towering cliffs, deep rift valleys, and terrain so uneven it would give even the bravest rover second thoughts about driving over it. These ridges showcase vast canyon systems, some plunging deeper than the Grand Canyon on land. Where fast ridges look smooth, slow ridges look like the planet tried sculpting with cold clay and decided it liked the jagged aesthetic. The Mid-Atlantic Ridge is one of the classic examples of a slow-spreading ridge. Its plates inch apart only a couple of centimeters per year, barely faster than your fingernails grow. Because of this, it has a pronounced central rift valley, steep walls, and dramatic topography that makes the landscape look like something out of a deep-sea epic. By contrast, the East Pacific Rise spreads several times faster. Its movement is so steady that the Central Valley barely has time to form. Instead, the ridge there looks more like a continuous volcanic swell, broad and gently sloping. The speed also affects how crust cools. Fast-spreading crust stays warm longer because new material constantly arrives to reheat the region. Slow-spreading crust cools more thoroughly, making it denser and less buoyant. This density difference contributes to the contrasting shapes between ridge types. Warm crust floats higher, cool crust sinks lower, exaggerating valleys and elevating peaks depending on the pace of spreading. Even the chemistry of volcanic eruptions changes with spreading speed. Fast-spreading centers tend to host more frequent, more uniform eruptions, producing long, fluid basalt flows that travel great distances. Slow-spreading centers have more episodic volcanic activity. Eruptions are sometimes isolated or focused in particular spots, often occurring after longer pauses that let pressure build. These differences influence everything from the thickness of the crust to the size and distribution of volcanic structures. Another curious effect of spreading speed is the way faults form. Slow-spreading ridges rely more on tectonic stretching because magma supply is insufficient to fully fill in the space. This stretching creates enormous faults that can lift blocks of crust into tilted platforms, adding more rugged steps to the ridge's architecture. Fast-spreading ridges don't need as much faulting. Magma does most of the work there. The terrain, therefore, is more stable and less broken. Spreading speed also impacts how vent fields develop, though not in the ways that might seem obvious. Fast ridges may host numerous small vent systems scattered over broad areas, fed by the consistent heat and continuous magma injections. Slow ridges, with their deeper valleys and complex fracture networks, may host fewer but more concentrated vent sites. Each environment creates different challenges for life, though that story belongs to entirely different parts of our journey. It's easy to imagine Earth's mantle acting like an indecisive treadmill operator, adjusting the ridge speeds according to some mysterious internal logic. But in reality, spreading speeds reflect the vast, interconnected dynamics of the mantle and crust. Forces so large and slow that we only comprehend them through careful measurement and the patterns left behind in the rocks. These variations are not flaws in the system. They are the system. They give the ridge personality, sculpt the oceans, influence volcanic activity, and ultimately shape the geography of the entire planet. What seems chaotic is, in truth, a beautifully orchestrated set of processes. Each ridge segment moves at its own pace, driven by deep forces that operate far beneath our feet. Some sprint, some stroll, and some behave like they're waiting for motivation to arrive. Together, they create the ever-evolving, ever-shifting face of the ocean floor. And while Earth's spreading treadmill may not offer a consistent workout, it certainly keeps geological life interesting. If the mid-ocean ridge is where Earth creates new crust, then deep ocean trenches are where it quietly swallows the old stuff. No ceremony, no announcement, just a slow geological gulp. These trenches form the darkest, deepest scars on the seafloor, plunging farther than the height of most mountains. They mark the locations where one slab of Earth's crust bends downward and begins its long descent back into the mantle. If the planet had a lost and found for misplaced crust, this would be it. The place where old seafloor goes when it's time to retire, renovate, or simply vanish into molten anonymity. At first glance, a trench sounds simple. One plate sinks, the other stays on top. But the process is far more intricate. When dense oceanic crust cools as it moves away from the ridge, it grows heavier and begins to sag like a tired shelf. Eventually, at the edge of a plate, this dense crust meets another plate. If the two collide and one plate is sufficiently heavier, it begins to bend and dip downward. This bending forms the beginning of a trench, a narrow, elongated valley so deep that sunlight might as well not exist. It's the ultimate geological drop-off point. The descent of an oceanic plate into the mantle is called subduction, a word that sounds gentle, almost polite, but describes one of the most powerful processes shaping Earth's surface. As the plate sinks, it drags the trench downward with it, carving increasingly steep angles and deepening the valley. In some places, these trenches plunge more than 11 kilometers beneath the surface. If Mount Everest were placed inside the deepest trench, its peak would still be a mile underwater. It's a reminder that the ocean has depths that laugh in the face of even our tallest mountains. But trenches aren't just holes in the ground. They are active, dynamic zones where immense forces collide. The bending of the sinking plate creates enormous tension, leading to cracks, faults, and tremors. Earthquakes are frequent along subduction zones, though most occur far beneath the ocean surface. The grinding, pushing, and crumpling of rock releases extraordinary amounts of energy. Some of the largest earthquakes ever recorded on Earth originated along trenches, where uncompromising physics forces two slabs of rock to negotiate positions like very stubborn roommates. As the descending plate sinks deeper, the pressure and heat increase. Water trapped within the minerals of the crust is squeezed out and rises into the overlying mantle. This addition of water lowers the melting point of the mantle rock, causing pockets of magma to form. These pockets, buoyant and eager, rise toward the surface, often creating volcanic arcs on the overriding plate. That's why many trenches are paired with chains of volcanoes on nearby islands or continents. Japan, the Aleutians, the Andes, and the Cascades all owe their fiery personalities to the presence of a trench pulling crust into the mantle. It's a strange relationship. The deeper the trench, the more dramatic the volcanism nearby. Geologically speaking, trenches are conveyor belts in reverse. They don't deliver new crust to the surface, they take it away. While the ridge system creates fresh seafloor, subduction zones consume it, pulling millions of square kilometers of crust downward over millions of years. Without trenches, the Earth would have nowhere to put all the crust being generated at the ridges. Continents would buckle, oceans would overflow with rock, and the crust might pile up awkwardly like an overstuffed drawer refusing to close. Fortunately, subduction zones keep the planet tidy, recycling old material and balancing the constant creation happening elsewhere. Trenches also help shape ocean circulation in subtle ways. Their steep walls and deep basins influence how water flows through the lower layers of the ocean. Dense, cold water moves differently around a deep trench than it does around a broad, abyssal plain. These subtle redirections can affect nutrient transport, oxygen levels, and the movement of sediment. The deepest trenches act as sediment traps, catching material drifting down from above and storing it in thick, slowly accumulating layers. Each layer is like a page in a history book, recording ancient volcanic eruptions, plankton blooms, or dust storms from continents far away. Yet for all their significance, trenches remain among the least explored parts of the planet. Their extreme depth makes them difficult to reach, and the pressure is beyond anything experienced in shallower seas. At the bottom of the deepest trenches, pressures exceed 1,000 times the normal atmospheric pressure at sea level. Even the sturdiest research submersibles must be engineered with extraordinary precision to survive those crushing forces. The deep trenches are not hostile out of malice. They're just the natural result of physics, balancing the weight of oceans and rock. Life does exist down there, though it is sparse, specialized, and adapted to the kind of conditions that would terrify almost any other organism on Earth. Certain amphipods, worms, and microorganisms live in these extreme depths, surviving in darkness, cold, and immense pressure. Their presence is a reminder that even in the deepest crevices where the crust bends toward oblivion, life still finds a foothold. Trenches are, in many ways, the planet's hidden underworld. They are places where the crust disappears from the familiar world and slips into the silent, molten realm below. They sculpt coastlines, shape island chains, trigger earthquakes, and fuel volcanoes. And despite being remote and rarely seen, they help balance the entire system of plate tectonics. Without them, Earth's outer shell would buckle uncontrollably. With them, the planet maintains a cycle of renewal and destruction that has persisted for hundreds of millions of years. It's almost charming to imagine trenches as Earth's lost and found box for wandering crust, places where slabs of seafloor go when their time is up. But unlike a real lost and found, the planet doesn't return what it takes. Instead, it melts it, recycles it, and eventually reuses the material in new eruptions miles away. In this grand cycle, trenches are not the end of the story. They are merely the doorway into the next chapter of Earth's geologic life. Marine volcanism is the kind of geological drama that unfolds in total secrecy. Quiet eruptions, slow-building mountains, and vast landscapes forming in darkness where no sunlight or applause ever reaches. Yet beneath the waves, volcanoes are some of Earth's most persistent architects. They mold the sea floor, create mountains that never breach the surface, and sculpt underwater terrains that stretch across oceans. Some eruptions manage to build entire islands from scratch, while others fall just a little short. volcanoes trying very hard to become islands, but not quite making the cut, like overachievers who stopped one chapter shy of finishing their autobiography. Most seamounts, those isolated underwater volcanoes that rise like lonely peaks from the abyss, begin their lives along the ridge system. There, magma wells upward from deep within the mantle, exploited by weaknesses in the crust. When that rising magma finds a focused spot to break through, it erupts. These eruptions don't resemble the explosive theatrics of land volcanoes. They occur under immense pressure, which suppresses the violence we associate with lava fountains or ash clouds. Instead, underwater eruptions typically involve lavas oozing, spreading, and chilling quickly into rounded shapes called pillow basalts. Bulbous, stacked formations that look like geological dumplings. Each eruption adds new layers to the nascent volcano. These layers build upward and outward, gradually forming a seamount. Depending on how much magma is available, how long the eruptions last, and how frequently new material rises, a seamount may grow for millions of years before slowing down or going dormant. The mantle plume beneath a ridge can supply magma for remarkably long periods, allowing volcanic features to mature into true giants. Some seamounts rise more than 3,000 meters above the surrounding seafloor, towering mountains in any sense, even if they never reach the surface. The moment a volcano comes close to piercing the ocean surface, however, the rules change. Wave action becomes a sculptor, reshaping the summit by eroding loose rock and redistributing sediment. Only the strongest, most continuously fed volcanic systems survive this onslaught long enough to break the surface and become islands. Most underwater volcanoes never make it past that threshold. They come tantalizingly close, just a few hundred meters short, but their magma supply dwindles, the eruptions cease, and erosion carves them back down. These near islands remain as tall underwater pinnacles, anonymous to the surface world, but monumental in the hidden geography below. As a seamount grows, it can also influence water flow. Currents encounter the steep slopes and are deflected upward or sideways, creating swirling eddies. These changes affect how nutrients move through the ocean, sometimes concentrating life around the volcano. Even dormant seamounts can act as ecological anchors for fish, corals, and drifting organisms that depend on the altered currents for food or shelter. But geology remains the architect here, directing the shape and size of each structure long before biology arrives. Not all seamounts form directly on ridge crests. Some originate slightly off-center, fed by fingers of magma branching away from the main upwelling zone. As the seafloor spreads, these volcanoes drift away from the ridge, like geological passengers, riding the conveyor belt of the ocean floor. Over millions of years, what once sat atop a magma source ends up far from it. The volcano cools, solidifies, and becomes extinct, a massive monument slowly sinking as the aging crust beneath it cools and contracts. Some seamounts are born in clusters, forming small, underwater mountain ranges of their own. These clusters can stretch across hundreds of kilometers, each peak representing a different stage of volcanic growth. The variability in size and shape tells a story of shifting magma pathways, changing crustal conditions, and the wandering motions of tectonic plates. Each volcano is a time capsule of eruptions layered atop one another, a vertical history of fire written beneath the cold ocean. The summit of a growing seamount is often a chaotic landscape. Even though the slopes below may be smooth, the top can possess craters, fissures, and jagged flows created by repeated eruptions. Lava erupting at depth cools so swiftly that it fractures, creating glassy, brittle surfaces. In some places, hydrothermal fluids seep through the cracks, depositing minerals that cement parts of the summit together. In others, the rock remains loose and prone to collapse. Entire sections of a growing volcano can slide down slope, creating landslides that travel for miles across the abyssal plains. As a volcano moves farther from its magma source, its eruptions become quieter and less frequent. Tall seamounts eventually settle into the role of extinct giants. Over time, the once sharp peak flattens, carved by waves if it ever rose near the surface, or worn down by erosion, landslides, and the steady accumulation of sediment if it never came close. Many old seamounts transform into guyots, flat-topped mountains, though that story belongs to another chapter entirely. Some of the most dramatic seamounts form not at ridges, but near tectonic hotspots, those deep, persistent plumes of heat rising through the mantle like slow-motion blowtorches. But even ridge-based volcanoes occasionally encounter small, hotspot-like anomalies that give them extra magma for a time, resulting in rapid growth spurts. These spurts can propel a volcano upward quickly, temporarily overshadowing its neighbours before cooling returns it to a normal pace. Marine volcanism is also responsible for building vast volcanic plateaus, broad regions where eruptions repeatedly flood the seafloor with lava over enormous areas. These regions may not form tall mountains, but they create thick layers of crust that shape the seafloor on continental scales. Though less flashy than seamounts, they represent some of the largest volcanic outpourings on the planet. Every seamount, whether tiny or colossal, active or extinct, contributes to the slow reshaping of the oceans. Some grow quietly, some collapse dramatically, and some, almost, but not quite, break through the surface to wave hello to the world above. Together, they compose an underwater mountain landscape built from eruptions no human has ever witnessed, a world where volcanoes rise in darkness and sculpt a terrain as dramatic as anything on land. In the deep sea, marine volcanism is the heartbeat of the crust, steady, powerful, and endlessly creative. Through its eruptions, seamounts rise like secret mountains, each one a reminder that Earth's most ambitious construction projects often happen in places no one can see. Somewhere in the vast quiet of the deep ocean lie mountains that look strangely unfinished. Tall, massive and proud, yet mysteriously flat on top, as if someone took a giant razor and shaved off their peaks. These are guyots, the flat-topped underwater mountains that once stood high enough for waves to crash across their summits. Long ago, they were islands, or at least hopeful candidates, rising above the sea surface with ambitions of staying there. But the ocean has a way of humbling even mountains. Over time, those ancient waves gave them what can only be described as a planetary haircut, before they slowly sank beneath the water and disappeared back into the deep. To understand how guyots form, imagine a newborn seamount, one of those volcanoes rising from the sea floor, growing eruption by eruption. If the magma supply is generous and the eruptions continue steadily, the volcano eventually pushes its summit above sea level. Suddenly, what was once dark and silent becomes an island surrounded by sunlight, waves, wind, and weather. For a time, the volcano enjoys a brief career in the world of surface geography, complete with beaches, cliffs, and whatever early life might have wandered ashore in past eras. But islands born of volcanism are temporary features, no matter how sturdy they appear. Once a seamount stops erupting, the balance between building upward and eroding downward shifts. Without new lava adding height, waves begin to bite into the rock. Storms batter the cliffs, Rain pours down into cracks. Rivers, if the island is large enough, begin to carve channels. Every force that shapes landscapes on land now turns its attention to the volcanic summit. Over thousands to millions of years, the island becomes lower, its sharp peak slowly leveling out. Near the surface, waves exert enormous power. They break down the uppermost rock, grind edges into smooth platforms, and transport materials away from the summit. Tides add their own rhythm of erosion. Eventually, the top of the volcano is shaved flat, leaving a broad, level surface just above or slightly below sea level. This smoothed region is known as a wave-cut platform. It is the future top of a guyot, the flat cap that gives these underwater mountains their iconic silhouette. But erosion is only half the story. The real transformation happens when the island begins to sink. As the crust beneath the volcano cools and moves away from the hot ridge where it was born, it becomes denser and gradually subsides. The entire volcanic structure rides this sinking elevator, dropping centimetre by centimetre over millions of years. Meanwhile, global sea levels change, shorelines shift, and the platform that once stood in the sun slowly descends into permanent darkness. By the time the island has completely submerged, the once visible summit is now hundreds or even thousands of meters beneath the surface. The flat top remains, preserved like a relic of the mountain's former life above the water. With enough time, sediment settles across the surface, smoothing it further. Coral reefs, if they existed on the original island, may leave remnants, now fossilized and buried beneath layers of deep ocean debris. What was once a wave-lashed shoreline becomes part of the abyssal plain's hidden architecture. Guyots vary widely in size. Some are small plateaus only a few kilometers across, while others spread over vast areas like sunken tablelands. Many rise several thousand meters from the seafloor, yet their perfectly flattened caps make them look oddly manufactured, as if placed there intentionally by a forgetful civilization. They appear as isolated mesas in the deep, a shape so unexpected that early ocean mappers were baffled when they first saw these profiles emerge from sonar readings. How could the tops of underwater mountains be so flat? It was a mystery until geologists realized that these formations were once islands, sculpted at the ocean's surface before sinking to their quiet, submerged retirement. The Pacific Ocean holds some of the most famous guyots, many of them part of long chains created as tectonic plates moved over volcanic hotspots. A hotspot produces a volcano. The plate shifts. The volcano drifts off the plume and goes extinct. Erosion flattens it. Subsidence sinks it, and eventually another volcano rises behind it to repeat the cycle. The result is a dotted line of guyots stretched across the seafloor like ancient stepping stones. The Emperor Seamount Chain, northwest of Hawaii, is a beautiful example. A procession of sunken giants, each one a reminder of a long-forgotten island kingdom. Though guyots no longer reach the surface, they are far from insignificant. Their massive bulk influences how deep currents flow. Water moving across the abyss encounters these submerged plateaus and is forced upward or sideways, altering patterns of circulation. Nutrients accumulate in the wake of these underwater mountains, creating hotspots of biological activity far above them. Fish migrate around their flanks, plankton drift along their edges, and larger predators may cruise nearby. Even extinct volcanic features can shape life in the oceans, millions of years after they last erupted. The flat tops of guyots also preserve valuable geological records. Sediment cores drilled from their summits contain fossils of organisms that once lived in shallow water, tiny pieces of evidence that these mountains once touched the sky relative to sea level. These fossils allow scientists to track ancient sea levels, climate shifts, and the movements of tectonic plates. Every guyot is a diary of Earth's past, written in limestone, basalt, and shell fragments. There is also something poetically humbling about guyots. They remind us that even mountains are transient. What rises high above the sea can be ground down, flooded, and carried into the deep. Their flat tops are scars of time, evidence of waves pounding a summit that no longer sees daylight. It's the ocean's quiet signature on the world's geology, a testament to power and patience working together. So the next time you imagine the deep ocean as a blank, featureless void, remember the guyots scattered across the sea floor. They are the ancient elders of the ocean, mountains with stories etched into their plateaued crowns. Though waves once gave them a thorough haircut, their flat summits now rest in eternal darkness, silent monuments to the shifting, rising, sinking world above. If you could sit quietly on the deep seafloor, ignoring the crushing pressure, total darkness, and general inconvenience of being several miles underwater, you'd notice something surprising. The ocean floor is not the peaceful, motionless world it pretends to be. Beneath that calm layer of water, tectonic plates are constantly shoving, tugging, stretching, and grinding against one another. And every so often, they stop pretending to get along. When the tension snaps, the plates unleash a burst of seismic energy so abrupt and so forceful that it ripples through the deep like a planetary temper tantrum. These are fracture-driven earthquakes, Earth's crust arguing louder than neighbours at 2 a.m, only there's no landlord to call and no polite note to leave on the door. Earthquakes along fracture zones begin with stress, immense stress, built slowly and silently as tectonic plates move at different speeds or directions. Along ridge systems, spreading creates cracks that extend outward, forming massive crease lines across the ocean floor. These fracture zones act like geological scars, preserving the memory of ancient plate motions. Although only a short portion of each fracture zone actively slips today, the entire structure exists because plates once moved differently at various points along the ridge. That legacy of motion leaves behind weaknesses, faults where rocks are prone to shifting suddenly when pressure builds to its breaking point. Under the sea, these quakes don't produce the dramatic, surface-visible ruptures we associate with land-based earthquakes. Instead, they generate seismic waves that travel through solid rock, water, and sediment. Most of these tremors go entirely unnoticed by humans, unless they occur close to populated coastlines or are strong enough to trigger tsunamis. But even the smaller ones, those that don't disturb the ocean surface at all, can be powerful in their own environment. They rattle the crust, rearrange cracks, displace sediments, and sometimes even trigger small landslides along steep seafloor slopes. Fracture-driven earthquakes differ from subduction zone quakes in important ways. At subduction zones, plates dive beneath one another, creating deep, powerful quakes at great depths. Along transform faults connecting ridge segments, the motion is mostly sideways, a horizontal grinding motion that builds stress very slowly. These quakes occur at relatively shallow depths, usually within the upper few kilometers of crust. The shaking tends to be sharp and sudden, like snapping a thick board. And because the crust here is younger and thinner than in other tectonic environments, it fails quickly once enough strain accumulates. The tension that leads to these quakes is the direct result of plates spreading unevenly. Ridge segments don't move at the same speed, and the transform faults between them accommodate the differences by slipping periodically. Think of 2 conveyor belts running parallel, but at slightly different speeds. If a rigid frame forced them to stay connected, tension would build until something cracked. That's essentially what happens beneath the ocean. The crust remains locked until the stress becomes unbearable. Then, in an instant, the fault slips and energy radiates outward. Sometimes the energy release is so minor that only sensitive seismic instruments detect it. Other times, the force is large enough to send vibrations across entire ocean basins. These quakes can transmit through hundreds or thousands of kilometers of rock, bouncing, refracting, and traveling along the crust mantle boundary. For scientists, these seismic waves are a gift. By measuring how fast they travel and how they bend, researchers can create detailed maps of the Earth's interior, revealing layers, densities, and even temperatures long before any drilling tool could ever reach them. In the immediate vicinity, however, the effects are far more physical. A significant quake can jolt hydrothermal systems, causing vents to sputter, redirect, or temporarily shut off as cracks seal or form anew. It can send clouds of sediment billowing into the dark, smothering some organisms while revealing new surfaces for microbial life to colonize. Fish and deep-sea creatures that rely on vibrations to navigate or communicate may momentarily scatter in confusion. Even the deep-sea landscape itself can shift as faults move, ridges adjust, and blocks of crust tilt ever so slightly. Despite their power, these quakes rarely cause tsunamis, because transform motion involves horizontal sliding rather than vertical heaving. The water above isn't displaced dramatically enough to form large waves. Only in rare cases, when a quake triggers a landslide, or when a fault has some vertical motion, does a tsunami result. For the most part, fracture-driven quakes shake the ocean floor without disturbing the surface, conducting their noisy arguments where only geologists and deep-sea creatures are listening. The study of these earthquakes reveals another critical detail. They help regulate the pace of plate tectonics. Faults relieve stress in bursts. Without these sudden releases, the crust might bend or deform more catastrophically. Earthquakes, inconvenient as they are for structures on land, serve as safety valves for the planet. They keep the crust moving at the slow, steady pace that defines plate tectonics, without letting strain accumulate to destructive extremes. In essence, the ocean floor grumbles so it doesn't break apart entirely. The seismicity along fracture zones also helps scientists estimate spreading rates. By measuring the number, magnitude, and timing of quakes, researchers can infer how rapidly strain accumulates and how often it gets released. These observations, combined with magnetic striping and bathymetric mapping, allow scientists to reconstruct millions of years of plate motion. Each quake adds another data point in the planet's long, ongoing narrative of drifting continents and shifting oceans. But perhaps what makes these underwater quakes most compelling is how quietly they influence the planet. They adjust the architecture of the seafloor, open and close pathways for chemical exchange, alter the shape of ridge segments, and create subtle changes that ripple through the deep. They operate invisibly, far from the human world, yet they help shape the very crust we stand on. So while fracture-driven earthquakes might sound like minor footnotes in the grand story of plate tectonics, they play essential roles, adjusting, accommodating, relieving stress, and keeping the ocean floor in constant motion. And even though we rarely hear them from the surface, down in the abyss, these events echo loudly. Tectonic plates arguing in deep, resonant tones that would definitely get a noise complaint if anyone lived nearby. Fortunately for them, and for us, the deep sea has no walls, no neighbours, and no landlord to intervene. The arguments continue, the faults slip, and the ocean floor reshapes itself, piece by drifting piece, in the eternal rhythm of a restless planet. For most of human history, the ocean floor was the world's most committed introvert. perfectly content to remain unseen, unknown, and unbothered. But modern scientists, being the persistent creatures they are, decided that secrecy was no longer an option. Armed with new tools, new techniques, and a strong refusal to let a few thousand meters of water get in the way, they began mapping the seafloor with a determination that bordered on parental. Today, thanks to sonar and satellites, we can visualize underwater mountains, valleys, ridges, and trenches with remarkable clarity, essentially taking selfies of the seafloor from space, because Earth apparently wanted to update its geological profile picture. The most detailed technique available to scientists is multi-beam sonar, a technology that turns ships into underwater photographers. Multi-beam sonar works by emitting sound pulses downward in a fan-shaped pattern. These pulses travel through the water, bounce off the seafloor, and return to the ship's array of sensors. By measuring how long the echoes take to come back, scientists calculate the depth of the ocean floor at thousands of points simultaneously. The result is a sweeping image of the terrain below, built line by line as the ship moves forward. If single-beam sonar was like painting with a toothbrush, multi-beam sonar is like upgrading to a spray gun. Bigger strokes, finer details, and significantly less. Shouting into the void, hoping for a response. But sonar has its limitations. Sound travels beautifully underwater, but ships cannot wander across every square kilometre of the global ocean. That would require time, fuel, and an international fleet dedicated solely to ocean mapping. So scientists turned to satellites, which, despite being very far away from the seafloor, have an astonishing ability to detect its shape. They do this by measuring the height of the ocean surface with extraordinary precision. It might seem counterintuitive, but water doesn't lie flat. It dips slightly over deep trenches, bulges slightly over seamounts, and curves subtly in response to gravitational differences caused by underwater features. By tracking these tiny variations, changes as small as a few centimeters, satellites infer the shape of the seafloor below. Think of it like this. The seafloor tugs at the ocean's surface, the way magnets tug at iron filings. Satellites orbiting hundreds of kilometers overhead can detect this tug, convert it into data, and create maps that reveal major underwater structures. They can't see fine details, but they can outline entire mountain chains, trenches, plateaus, and fracture zones. It's remote sensing at its most ambitious, mapping a world no human eye can directly see by watching the water's surface wrinkle ever so slightly. Combining sonar and satellite data gives scientists a layered understanding of the ocean floor. Satellites provide broad, global coverage, highlighting the major features worth exploring. Ships equipped with sonar then fill in the gaps with high-resolution detail. It's a partnership that has transformed our understanding of the deep. Before these technologies, the ocean floor was a vague sketch, mostly blank, with the occasional guessed at feature scribbled in like a cartographer's wishful thinking. Now it's a landscape rich with detail, brimming with ridges, faults, volcanoes, and scars that reveal its tumultuous history. One of the most remarkable advances in seafloor mapping has been the shift from depth points to full-terrain models. Instead of a handful of measurements scattered across the ocean, we now produce three-dimensional topographic maps that show the contours of the seafloor with remarkable realism. These models allow scientists to visualize underwater features as if the water were drained away, an impossible but thrilling perspective. Suddenly, mountains rise from once forbidden depths. Valleys cut through long submerged plains. Volcanoes stand tall in the abyss, with calderas, slopes, and lava flows all visible through the textured mapping. These maps aren't just for admiring geology. They play critical roles in climate research, ocean circulation studies, tsunami modeling, fisheries management, and deep-sea exploration. The shape of the seafloor influences how currents travel, how heat moves, and how nutrients circulate. Without accurate maps, our models of the ocean, and therefore our models of the climate, would be riddled with guesswork. Seafloor mapping allows scientists to see how deep ridges deflect currents upward, how trenches redirect cold water, and how hidden peaks create swirling eddies that mix the ocean layers. Mapping also helps guide exploration. Scientists use high-resolution maps to identify promising areas for biological research, geological sampling, and even the discovery of new hydrothermal vent fields. The ocean is far too large to search blindly, so maps act like treasure outlines, revealing where the seafloor's most intriguing secrets might hide. Without these maps, many of the environments we now study, vent fields, seamount ecosystems, fracture systems, would still be undiscovered in the darkness. The newest frontier of mapping involves autonomous vehicles. These robotic explorers, untethered and outfitted with sonar and cameras, glide through the deep, collecting data where ships cannot go. Some are small enough to navigate steep ridges or narrow canyons. Others dive to extraordinary depths. They can operate for days or weeks at a time, gathering detailed images and returning with high-resolution maps of regions previously untouched by human technology. These robotic cartographers are expanding our understanding of underwater terrain faster than any ship could. And as technology advances, the ocean floor becomes less of a mystery. Yet it still holds far more unknown than known. Even now, despite satellites and sonar and robotic mapping, more than 80% of the seafloor remains unmapped in high resolution. In some areas, the best available data is still decades old. The deep sea is simply too vast to map quickly, but progress marches on, ping by ping, pixel by pixel. There is something poetic in this process. Scientists hovering above the waves, scanning the ocean surface for clues about what lies miles below. It's a reminder that curiosity, technology, and persistence can reveal even the most stubbornly hidden landscapes. As we continue to map the deep, the Earth slowly unveils its secret architecture, ridge after ridge, valley after valley, one sonar pulse and one satellite selfie at a time, deep beneath the surface, far below the reach of storms and sunlight. The mid-ocean ridge sprawls across the seafloor like a colossal barricade system. And just like hallways, shaped by stubborn architecture, the ocean's currents have no choice but to navigate around these underwater mountains. They flow where the ridges allow, accelerate where the slopes funnel them, and bend their paths when forced. In a realm with no walls, no doors, and no ceilings, the seafloor's topography becomes the closest thing the deep has to strict hall monitors. Underwater mountains bossing ocean water around with silent, immovable authority. To understand how ridges influence currents, you have to picture the ocean not as a uniform body of water, but as a layered, dynamic system with its own traffic rules. Currents at the surface follow the wind, guided by storms, temperature differences, and the rotation of the planet. But the deep ocean plays by different rules. Down there, water moves in slow, dense rivers shaped by pressure, gravity, and the contours of the seafloor. And nowhere does the terrain matter more than along the mid-ocean ridge. These underwater mountains rise thousands of meters from the abyss. They may not breach the surface, but they are tall enough to split deep currents into separate branches, funnel them through narrow gaps, or deflect them sideways along the flanks of the ridge. Imagine a massive river flowing across a plain. If a mountain unexpectedly appears in its path, the river doesn't go through it. It goes around. The same is true for deep ocean currents. They encounter the ridge, pause, feel inconvenienced, and then choose a new direction based on the available passages. The process happens slowly, quietly, and with the patience only water and geology possess. Water masses travelling through the deep ocean are influenced by density differences. Cold, salty water sinks, while warmer or fresher water stays higher. One of the densest water masses on Earth forms near the poles, where frigid temperatures and high salinity cause water to plunge downward. These heavy waters then creep along the seafloor, spreading from one ocean basin to another. Their journey is long, spanning thousands of miles, and the ridge acts like a giant sprawling set of toll gates they must pass through. But the ridge is not a single wall. It's a discontinuous, uneven chain broken by transform faults, fracture zones, and occasional deep passages. These openings, known as fracture zone valleys or deep gaps, allow currents to slip from one side of the ridge to the other. They are the rare doorways in an otherwise formidable barrier. The shape, depth, and width of these gaps determine how much deep water can pass through and at what speed. In this way, the ridge acts like the world's largest traffic regulator, shaping the routes taken by the coldest, most nutrient-rich waters on the planet. When deep currents interact with the ridge, they don't merely redirect, they mix. As water flows up and over seafloor slopes, it becomes destabilized. This vertical motion stirs layers of water that normally remain separate. Mixing is crucial to the ocean's health. It redistributes nutrients, oxygen, and heat. Without the turbulence caused by seafloor features like ridges, large portions of the deep ocean would become stagnant. Instead, the ridge injects motion into the deep in the same way a spoon stirs a thick soup. Slowly, but with undeniable effect. In some places, the ridge enhances upward movement of water, lifting deep, nutrient-loaded water toward the surface. This process, known as upwelling, feeds plankton blooms and supports entire food webs. While most upwelling near coastlines is driven by winds, deep ocean upwelling is often triggered by the shape of the seafloor. A ridge slope can act like a ramp, gently nudging deep water upward. Though the rise may be only tens of meters at a time, over vast distances it adds up, helping nutrients return to the surface layers where sunlight can fuel photosynthesis. The ridge also affects mid-depth currents, including those forming part of the global ocean conveyor belt. This vast system of interconnected currents transports heat around the planet, regulating climate over long timescales. While atmospheric conditions drive the surface portion of the conveyor belt, the deep portion relies heavily on seafloor topography. The pathway of this deep circulation is not smooth. It is shaped, slowed, and steered by the underwater mountains. Without the ridge, the conveyor belt would be far less organized. Water might stagnate in basins or take inefficient detours. Instead, the ridge creates a guided path, channeling deep water in ways that keep the system functioning like a global heartbeat. In some regions, the ridge interacts with currents to create swirling underwater vortices. These eddies can span hundreds of kilometers and last for months or years. They trap water masses inside their rotating walls, transporting heat and nutrients across ocean basins like wandering pockets of preserved conditions. Some eddies even carry chemical signatures from hydrothermal vent fields, spreading minerals far beyond their source. Satellites have revealed subtle fingerprints of these interactions at the surface. Even though the ridge lies miles below, its influence sometimes alters the height and shape of the sea surface by small but measurable amounts. These variations reflect changes in density and temperature, driven by deep currents forced to navigate around underwater obstacles. It's a reminder that the ridge, though invisible to the naked eye, shapes the ocean from the bottom up. Comparing the ridge to hall monitors might sound humorous, but the metaphor fits better than expected. The ridge sets boundaries. It enforces order. It directs movement. Water can grumble all it wants, but in the end, it must follow the paths carved by the mountains beneath it. And as the currents obey these silent rules, they help regulate climate, support ecosystems, and distribute life-sustaining nutrients through the ocean. In the end, the mid-ocean ridge is not just a geological feature. It is a quiet conductor guiding the ocean's circulation. Its invisible influence ripples through the deep, shaping the movement of water masses that affect everything from polar climates to tropical fisheries. It is the ocean's great organizer, the backstage architect, ensuring that the show above runs smoothly. And all the while, it stands firm beneath the waves, ancient, sprawling, and absolutely committed to bossing the world's water around with unshakable confidence. For all their dramatic landscapes and restless geology, ocean ridges also perform a subtler but immensely important job. They help season the ocean. Not with spices, of course, but with minerals, elements, and chemicals that quietly shape the composition of seawater. If the ocean were a giant pot of soup, the ridges would be the mischievous chefs tossing in new ingredients from below, with minerals sneaking into the ocean like flavor packets that dissolve before anyone notices who added them. These chemical contributions may seem invisible, but their impact ripples through the entire marine world, influencing everything from nutrient cycles to long-term climate patterns. To understand how ridges influence seawater chemistry, we need to revisit the extraordinary interaction between seawater and the newly formed crust. When cold, dense ocean water percolates down through cracks in the seafloor, it encounters rock heated by underlying magma. The water warms rapidly, dissolving minerals and metals as it travels deeper. But it doesn't stop at simply dissolving things. It also transforms. Chemical reactions between the water and hot rocks alter the water's composition dramatically. By the time it re-emerges through hydrothermal vents, the fluid is no longer seawater in the way we know it. It has become a concentrated solution of compounds pulled from the crust. These hydrothermal fluids are one of the major pathways through which ridges add chemicals to the ocean. When vent water gushes into the surrounding sea, it cools and mixes, releasing metals, sulfides, and other compounds. Many of these minerals react immediately, forming particles that drift like tiny snowflakes in the dark. Others dissolve fully into the seawater, becoming part of the chemical tapestry that supports life. Over millions of years, these contributions accumulate. Hydrothermal venting has added untold quantities of iron, manganese, and other trace metals to the ocean, materials that organisms in even the most distant waters rely upon. But vents aren't the only contributors. The crust itself participates in this chemical exchange. Newly formed basalt at the ridge cools rapidly in contact with seawater, locking certain elements into the rock while releasing others back into the surrounding water. Magnesium, for instance, is stripped from seawater at high temperatures and incorporated into the altered crust. In exchange, the crust releases calcium. This trade alters the ocean's balance of ions, a delicate dance of chemistry that has continued for hundreds of millions of years. These interactions also affect the carbon cycle. Hydrothermal systems can remove carbon dioxide from seawater by converting it into carbonate minerals within the crust. At the same time, They inject reduced carbon compounds into the deep ocean, providing fuel for microbial life that forms the foundation of vent ecosystems. Though small on short timescales, these exchanges add up on geological ones, helping regulate the ocean's long-term carbon budget. Even the temperature of seawater plays a role in these chemical transformations. When hydrothermal fluids mix with cold deep water, they cause certain minerals to precipitate instantly. Iron sulfide forms the dark plumes seen above black smokers. Silica precipitates around white smokers. These precipitates settle out over time, forming metal-rich sediments that can blanket the seafloor. But a surprising portion of these particles dissolve again as they drift into the open ocean, adding nutrients and trace elements to waters far from the ridge. The influence of ridges extends beyond hydrothermal processes. Volcanic eruptions at the ridge release gases into the ocean: hydrogen, methane, carbon dioxide, and small amounts of other volatile compounds. These gases dissolve and react with seawater, sometimes fueling microbial communities that thrive on their chemical energy. Methane, for example, becomes food for specialized bacteria that convert it into biomass, linking geology directly to biology. Iron, one of the most important trace metals in the ocean, is supplied in part by ridge activity. In many regions, iron limits biological productivity. Tiny phytoplankton floating near the surface need iron to photosynthesize. Without sufficient iron, they cannot grow, even if all other nutrients are abundant. Hydrothermal vents, though located far below the surface, send iron-rich particles into the deep ocean. Some of these particles remain suspended long enough to enter global currents and travel thousands of kilometers before eventually reaching sunlit waters. When they arrive, they act like micronutrient supplements, stimulating plankton blooms in regions where the ocean is otherwise starved of iron. In this way, ridges indirectly influence the amount of carbon absorbed by the ocean. When plankton grow, they take in carbon dioxide. When they die, some of that carbon sinks to the deep ocean, effectively locking it away. Thus, the chemical contributions from ridges ripple outward from the deep to the surface, shaping the planet's carbon cycle and impacting the climate. The chemistry of seawater is further shaped by ridge-related alteration of sediments. Warm fluids circulating through the crust can move into nearby sediments, altering them chemically and fundamentally changing how elements, such as phosphorus or silica, behave. These processes influence how readily sediments trap or release nutrients over time, affecting ecosystems far removed from the ridge itself. Even the pH of seawater has links to ridge processes. Hydrothermal systems can remove or release hydrogen ions, subtly shifting acidity in localized regions. While these changes rarely affect the broader ocean, they demonstrate how deeply intertwined water and rock are beneath the surface. As scientists continue to study these interactions, new discoveries constantly reshape our understanding. Robotic expeditions have revealed vent fields with unusual mineral compositions. Some vent systems produce fluids rich in rare earth elements. Others generate organic molecules that hint at connections between geology and the origins of life. Each new site expands our appreciation for the complexity of chemical exchange at the ridge. It's a reminder that the ocean's chemistry is not static. Far from it. It is fed, stirred, altered, and flavored by countless processes, from the mundane mixing of currents to the explosive birth of new crust. And ocean ridges, with their hydrothermal plumes and reactive rocks, remain some of the most important contributors. So the next time you look out at the ocean and see nothing but blue, remember that deep below, the seafloor is busy, adding its own ingredients. Minerals slip into the water quietly, like shy flavor packets waiting to dissolve. Chemical reactions brew unseen, and the ocean, ever dynamic, carries these contributions around the world. Proof that even the darkest, most hidden landscapes can shape the chemistry of life above. The deep ocean has always been humanity's final stubborn frontier. A place so inaccessible that for most of history, it might as well have been on another planet. But now we're entering an era in which the deep sea is no longer a silent mystery. Robotic explorers, autonomous subs, and high-tech probes are marching, or more accurately gliding, into the abyss. And as they descend into landscapes no human has ever seen, they do so with the endearing clumsiness of slightly confused tourists, wide-eyed cameras, blinking lights, and a vibe that says, "We're not entirely sure what we're looking at, but we're very excited to be here." These next-generation robots are nothing like the early submersibles that creaked ominously and needed constant babysitting. Today's deep-sea explorers are sleek, intelligent, and increasingly independent. Many of them operate without tethers or surface guidance. They navigate using sonar, onboard computers, and sensors that help them build maps in real time. They can adjust buoyancy, avoid hazards, and even make decisions about which features are worth further investigation. They're not thinking in the human sense, of course, but their internal programming gives them an almost personality-like determination. Drop them into a trench or along a ridge, and they begin scanning dutifully, like tourists clutching guidebooks and checking every landmark off the list. One of the rising stars of deep-sea exploration is the Autonomous Underwater Vehicle, or AUV. These torpedo-shaped robots can travel for hours or even days, tracing intricate patterns along the seafloor. Equipped with multi-beam sonar, chemical sensors, and high-definition cameras, they gather data that ships could never collect on their own. Some AUVs fly only a few meters above the ground, skimming over volcanic slopes and vent fields with an elegance that belies the harsh environment. Others dive deep into trenches, bringing back unprecedented images and measurements from places where pressure would crush almost anything else. Then there are remotely operated vehicles, or ROVs, the tethered cousins of the AUVs. If AUVs are the explorers, ROVs are the meticulous scientists, descending with mechanical arms, capable of picking up rocks, taking biological samples, or placing instruments directly on the seafloor. A skilled pilot on a ship guides the ROV through rugged terrain, swiveling cameras and manipulating tools as if performing surgery in complete darkness. ROVs have uncovered hydrothermal vent fields, filmed bizarre deep-sea creatures, and collected rocks from volcanic slopes, all while operating in an environment where human presence would be impossible. Newer ROVs are increasingly sophisticated. They have articulating limbs, precise grippers, and gentle suction devices that can collect delicate organisms without harming them. Some even carry small laboratories, allowing scientists to analyze samples while still underwater. It's like sending down a miniature research station, one that knows how to hover, pivot, and occasionally stumble upon discoveries no one expected. But the future of deep-sea exploration isn't limited to just these traditional robotic platforms. Scientists are developing swarms of smaller submersibles, each designed to tackle a specific task. One may map a vent field, another may measure chemical plumes, and a third may document wildlife. Together, they operate like a coordinated team. Tiny robotic tourists taking group photos of geological wonders. These swarms can cover vast areas quickly, making them ideal for studying environments that change rapidly or span great distances. Upcoming missions are pushing boundaries further than ever. Some involve long endurance vehicles capable of remaining at depth for months. These subs lurk quietly near vent fields or ridge segments, monitoring temperature changes, seismic activity, and chemical fluctuations. They send data back to surface buoys, which transmit the information via satellite to scientists on land. It is continuous, real-time observation of environments we once saw only in fleeting glimpses. It's as though the ocean finally agreed to live stream its geology. Other missions aim to explore regions nearly untouched: deep rift valleys, remote seamount chains, and poorly mapped ridge segments hidden far from shipping lanes. There are plans to revisit known vent fields that have changed dramatically since their initial discovery. New eruptions may have occurred, vents may have shifted, and entire communities may have reorganized themselves. Robotic subs will be there to capture those stories, the geological and biological dramas unfolding in the dark. Perhaps the most ambitious missions are those dedicated to drilling and sampling beneath the seafloor. In these expedition plans, robotic drills or hybrid vehicles penetrate volcanic crust, retrieve cores, and search for microbes living within the rock itself. These missions could reshape our understanding of the deep biosphere, life that exists miles below the surface, fueled by chemical reactions rather than sunlight. Not surprisingly, space agencies are taking notes. The technologies perfected in deep-sea exploration, pressure-resistant materials, autonomous navigation, chemical sensing are exactly the tools needed to explore oceans on other worlds. Moons like Europa and Enceladus may harbour subsurface oceans beneath thick ice shells. The robots we send into Earth's deep ocean today are prototypes for the explorers we may one day send across the solar system. In a strange twist, studying Earth's ocean may help us discover life beyond it. But for all the sophistication of these machines, there's still an unmistakable charm to their missions. When a robot drifts into a dense cloud of vent minerals, its cameras blink like wary eyes. When it reaches a cliff edge and pauses before descending, it looks almost contemplative. And when it trundles across a ridge and bumps gently into a boulder, you can almost hear it saying, "Oops," in a very polite robotic accent. These machines represent the future of deep-sea science. A future where exploration becomes continuous, where discoveries become routine, and where the deep ocean slowly transforms from mysterious to mapped. Yet even as our robotic tourists become smarter and more capable, the ocean remains vast and full of surprises. They may be confused tourists for now, but each journey brings them, and us, closer to understanding a world that still refuses to reveal all its secrets at once. The next chapter of exploration is just beginning, and the robots, blinking lights and all, are already heading into the dark with unshakable enthusiasm. When we picture Earth's great landscapes, our minds go to the familiar: towering mountain ranges draped in snow, deserts rippled with wind-etched dunes, forests stretching so far the horizon has to squint to keep up. But the truth is, some of Earth's most spectacular terrain isn't in any postcard rack, travel blog, or airplane window view. It lies deep beneath the ocean, vast, rugged, pulsing with geological life, hidden in permanent darkness, where only pressure, rock, and time keep company. These submerged mountain ranges are the quiet architects of our planet, shaping everything from the chemistry of seawater to the path of global currents to the very outline of continents. And the ocean, like someone with an impressive yet immensely private hobby, keeps all this grandeur tucked away where only the most determined explorers ever glimpse it. Reflecting on the mid-ocean ridge system and all its branching structures, feels like reflecting on the Earth's innermost heartbeat. Under the pressure of miles of water, the crust is constantly created, stretched, twisted, cracked, vented, cooled, and finally recycled somewhere far away. This isn't a static landscape frozen in ancient time. It's a living system, a churn, a cycle, a quiet revolution happening at geological speed. The ridges are the starting line of new crust, places where molten rock rises to form mountains that grow outward, changing the shape of the ocean floor grain by grain. Even from the surface, where the world seems calm, you're floating above one of Earth's busiest construction zones. What makes these ridges even more extraordinary is how deeply they influence the world above them. Ocean currents, the ones that regulate climate, carry nutrients, and define marine ecosystems, are pushed and pulled by the contours of the ridge. Water is rerouted, stirred, lifted, or allowed to sink, depending on what the seafloor dictates. Entire global systems, from weather patterns to fish migrations, owe part of their behavior to underwater peaks that no sunlight ever touches. The chemistry of the ocean is sculpted there too. Minerals stream from hydrothermal vents like hidden chemical factories, mixing silently into the deep. These elements go on to support microscopic life, build shells, seed currents with vital nutrients, and form the invisible scaffolding that marine food webs rely on. Without ridges injecting their mineral fingerprint into the sea, the oceans would be chemically poorer, biologically emptier, and perhaps unrecognizably different. And then there's the astonishing diversity of life clinging to these ranges, thriving in places where logic once insisted life should not exist. Creatures congregate around vents, ridges, cliffs, and valleys carved by spreading crust. They build ecosystems without light, communities without sunlight, and food webs powered by chemistry rather than photosynthesis. These organisms are living proof that life adapts to the strangest and harshest environments, turning even superheated, mineral-laden waters into thriving neighborhoods. The ridges are not just geological wonders. They are biological crucibles. Even the quieter features, fracture zones stretching like scars, seamounts rising from darkness, guyots with their wave-shaved crowns, tell stories that echo across geologic time. They reveal where plates once touched, where islands once stood, where volcanoes once erupted, where ocean floors shifted shape. They are the fossilized memories of the planet's long, restless journey, preserved not in rock walls we can hike to, but in landscapes we must send robots to visit. In recent decades, our ability to map, explore, and observe these hidden mountains has grown dramatically. With sonar sweeping across the seafloor and satellites measuring subtle swells in the ocean surface, we now see patterns, lines, and structures once completely unknown. Robotic submersibles glide along ridge crests, through rift valleys, and past vent chimneys, documenting landscapes that earlier generations never dreamed existed. Slowly, patiently, pixel by pixel, Earth is letting us peek at the blueprints of its interior architecture. And yet, despite all we've learned, these mountains remain fundamentally mysterious. They stretch across the entire globe, but only small sections have been observed directly. Vast areas still lie unmapped in fine detail, entire ridge segments unexplored, enormous vent fields undiscovered. The ocean protects its secrets well. Every expedition uncovers something new, a vent that wasn't there 10 years ago, a volcano quietly growing in the dark, a creature with adaptations so strange it upends assumptions about biology. For all our technology, the deep remains a place where humility is required and surprise is expected. Reflecting on this hidden world, it's remarkable to realize how profoundly it shapes the visible one. Weather patterns, coastlines, nutrient cycles, marine life, continental drift, even the chemistry of the atmosphere. Each one depends in some way on processes unfolding along submerged mountain chains no human eye will ever see unaided. The mid-ocean ridges are the backstage crew running the entire show, adjusting everything quietly, while the surface world applauds the visible actors. And maybe that's why this closing chapter feels less like an ending and more like an invitation. The ridges, vents, trenches, and fracture zones will outlast us. They will continue to build, shift, cycle, and reshape the deep long after our maps and instruments fade. But now, at least, we know they're there. We know the planet's most spectacular landscapes aren't always the ones painted in sunlight. Sometimes they lie hidden in darkness, sculpted by fire and cooled by time, waiting patiently for us to discover them. In the end, it's both poetic and slightly comedic that Earth's greatest mountain ranges, its wildest slopes, tallest peaks, and longest chains, aren't the ones we photograph on vacations. They're the ones it keeps beneath miles of water, tucked away like a secret hobby the planet only shares when we insist on looking. And the more we peer into that darkness, the more extraordinary that secret becomes.